In this video, we'll talk about the heart of the receiver, a sampler, which is also called a comparator, decision slicer, or decision maker. The fundamental requirements of the sampler must be high sensitivity and low power, along with a clocking control when you should take the data information. Therefore, we will summarize why you need a high sensitivity and low power clock sampler, comparator, decision slicer makers. If the sampler's usage is for SerDes, we need to know what the goal of the SerDes is. For those data bits, what would you like to achieve? Think about the big error images for 5 seconds. Yes, you like to receive the same bits as what has been sent, which implies the correct data. For example, 1011.011 was sent, so you should expect to receive 1011.011 here. Or, to be straightforward, no error or very low bit error rate during the transmission is your goal. But the most critical block that could make a wrong decision is the sampler. That was the reason we mentioned the sampler is the heart of the receiver, which must sit at the RX front end operating at the maximum speed over serial data rate before downsampling the parallel data. Do you have any idea why the speed would make the sampler difficult to make the right decision? Think about the timing and signaling images for 5 seconds. Correct. Let's look at our best tool, an eye diagram, to review the timing and signaling images one more time in a SerDes. First of all, from the timing images, the CK data sample 2 is better than the CK data sample 1 in getting the right decision. But as the speed goes up, the bit pair is smaller and that's difficult to keep optimal timing at CKDS2 or achieve the best timing margin than the wider bit pair. On the other hand, the sample voltage 1, VS1, is likely to have a less voltage margin than the CK sample voltage 2, VS2. Unfortunately, as the speed goes up, the channel loss will be higher at the same median, and the receiver input swing will be smaller for sure. Overall, the performance metric of the eye width and the eye height will be reduced in seconds and millivolts at a high speed. Therefore, we must optimize the sampler to gain a high sensitivity as the speed goes up. What is the sensitivity mean? Think about the tolerable input swing for 5 seconds. Bingo! The input sensitivity means the input differential swing is Vs and minus Vs peak will be resolved or converted to VDD and ground respectively. Since the swing amplified or regenerated to a full swing would take time, if the bit pair is shorter than the sampler's regeneration time, the output of the sampler DL won't get to the full real VDD and ground level. On the other hand, if the bit pair is longer than the sampler's regeneration time, the output of the sampler DL should go to the full real VDD and ground level. This also explains the input sensitivity depends on the speed, and we could define the input sensitivity of the sampler to be the minimal tolerable input swing. For example, the minimal tolerable input swing is 25, 50, and 100 millivolts for the data rates of 5, 10, and 20 gigabit per second respectively. Equivalently, the minimal tolerable input swing is 25, 50, and 100 millivolts for the bit pair of 200, 150 picoseconds respectively. Please be advised, all the numbers here are unnecessary to be proportional linears, and that's just a simple image for everyone to understand easily. Is this minimal tolerable input swing the only one source of the sample's input sensitivity? Of course not. Think about the noise images for 5 seconds. Correct. From the iHigh link budget video, we will put the thermal noise into our design margin in the iHigh. Unfortunately, the thermal noise is unbounded, and we must evaluate the statistic characteristic to get the peak noise from the mean and standard deviation values. Then, the peak noise amplitude will depend on the observation time window over the number of bits, which is corresponding to the SerDes transmission goal, bit error rate. For example, if the mean equals 0, RMS voltage noise equals 1 mV, the minimal input sensitivity should add 14 mV and 16 mV to our previous values for the bit error rate equals 1e-12 and 1e-15 respectively. Again, for bit error rate equals 1e-12, the input sensitivity is 39, 64, and 114 mV for the data rate of 5, 10, and 20 gigabit per second respectively. Is that all? If your answer is yes, probably you need to review our iHigh link budget video one more time. Think about other deterministic noise images for 5 seconds. Right, the other contributors to the input sensitivity would be random DC offset and other bounded interferences. For the DC offset, it's a random mismatch, but we must add any DC offset calibration circuit to reduce it as small as possible. We'll talk about why we need a special DC offset cancellation for the sample later. But if we do, then we can reduce the offset as small as possible, and we could even ignore the residual offset to be roughly less than 1 mV. On the other hand, we may encounter the conversion from the common mode noise interference or crosstalk to the differential mode noise from the supply noise or high-speed signal coupling to the input, which are all called deterministic interference, since this coupling effect will be layout dependent in a deterministic way. We need to watch out for any parasitic analysis from the routing and don't be able to provide any number here. As a soft reminder, please watch out for all the toggling signaling line coupling to the sample input. After understanding why a high sensitivity sampler is needed, let's look at why you need a clock sampler. Think about the data sample and edge sample for 5 seconds. Correct. You could start with a clock data recovery CDR, which should use the samplers to get the data samples or edge samples as the early or late information in a band phase detector. After the CDR is logged to the input data, the edge clock CKE should align to the data transition, and the data clock CKD0, CKD1, etc. should sample the data A, B, etc. in the middle to recover the right data stream. Therefore, we only care about the sample data value at the clock sampling time instantaneously instead of value at other timing. Then, the clock sampler is a must instead of using other continuous time comparator like the OTA or op-amp. Lastly, after going through all the input sensitivity and clock sampling, do you have any idea why the power could be an issue? Right. The power of the clock sampler could be a concern since the input of the sampler is at the highest data rate in a link before downsampling to the pair data. In addition, the clock rate of the sampler is the highest clock rate in the receiver, even though you could apply half rate or quarter rate clocking architecture. A multi-phase clocking multiple samplers is a must, and the total samplers power is still high without reducing too much. For the full-rate band phase detector, you need 2 data samples and 1 edge sample. In addition, for full-rate DFE, you need 1 data sample and 1 error sample for the DFE application. If we have timing constraint in the DFE, we may need to apply loop unrolling DFE, and the DFE's number of samples is double. Usually, with the full-rate receiver at a very high speed, most people will need 7 samples, and the total power will go up if we did not pay attention to reducing the power of a clock sampler. Here are the summarized images of why we need a high sensitivity and low power clock sampler, which is the heart of the receiver, since it dominates the bit array in a high-speed SerDes. To achieve a very low bit array, we must sample the data at the center of the I/O with an input swing as larger as possible. Unfortunately, the churn loss scales with the speed, and the bit period in 1UI scale down with the speed respectively. Therefore, both the received input swing and the bit period would be too little to make the sampler generate the output rail-to-rail digital label within the bit period. That's the main reason that we need to improve the input sensitivity of a sampler applied to a high-speed SerDes. To achieve a high input sensitivity, first, we need to reduce its regeneration time at the target of a tolerable input swing. Second, we need to reduce its intrinsic thermal noise, which is unbounded and scale with the target bit array. Third, we need to reduce the residual input offset of the sampler after its DC offset calibration. Lastly, watch out any cause of CM to DM conversion due to any residual asymmetric in layout and external coupling source of toggling signaling is a must to increase the input sensitivity of the sampler. Again, both the data edge samples in a CDR shows us sample value at the data or transition at a specific timing is a must instead of other timings. Therefore, a clock in a sampler is a must to achieve the sample and hold functionality we need. Unfortunately, the clock sampler operates at the RX receiver front end under the high speed of the clocking and data. Also, the demands of the full-rate RX would be high, with 3 samplers in the CDR and 4 samplers in the loop unroll DFE. The sampler power will go up quickly, and we need to pay attention to any power overhead in the sampler design. I hope these images answer everyone's question about why you need a high sensitivity and low power clock sampler in a high-speed SerDes. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with the people who may be benefit from it.